Good morning, everyone. I hope that you're having a great week so far. We're going to finish off with radioactive decay today, and then we do not have any new lesson on Friday, which would mean Friday would be a good day for you to work on some of the problems in your final assessment. And then next week will be the final week of lessons, and we're going to have a lesson on Monday, which is dealing with half-life, and a lesson on Wednesday of next week dealing with fission and fusion. I originally had planned on doing one more lesson on the Friday, dealing with what's called the standard model of matter, but I've decided not to do that. I've decided that Friday will be the last day for you to put the finishing touches on your final assessments, so we're not going to be learning anything new that day. Anyway, we're going to finish off with radioactive decay today. This is on page 30 of your current handout. Last time we looked at alpha decay and at beta decay, and alpha decay involves the emission from a nucleus of 2 protons and 2 neutrons in the form of an alpha particle. We learned that beta decay is something that is very, very weird going on. What beta decay is inside of the nucleus, a neutron is transformed into a proton, an electron, and something called an antineutrino. And the electron, which is the beta particle, is emitted from the nucleus. So basically what happens during beta decay is a neutron changes into a proton. But we didn't talk about gamma decay, so that's what we're going to spend a few minutes talking about here today. Gamma decay occurs because the nucleus of a particular atom is unstable, but it's not unstable in terms of how many nucleons there are. Alpha decay is unstable because there are too many nucleons, so it spits out an alpha particle. Gamma decay occurs because the nucleus is unstable because the nucleons are not arranged very effectively or efficiently. They're not packed together as well as they could be. And as a result of that, we talk about nuclei having excited states, kind of like when we talk about atoms being excited, except this has nothing to do with electron energy levels. So when a nucleus is in an excited state, what that physically means is that the nucleons are farther apart than they would be in a less excited state. When a nucleus makes a transition to a lower energy state, what that means is that all of the nucleons will be more efficiently packed together. They will be closer together, in fact, and as a result of that, there is less energy in the system afterwards, and that energy is conserved due to the emission of a gamma ray photon. It's very similar to a photon being emitted when an electron moves to a lower energy level within an atom. However, when we talk about the energy states of a nucleus, the numbers are a lot bigger. This is not in your note package, but this is a diagram I pulled, I believe, from your textbook. It shows the nuclear energy levels. So we're not talking about electron energy levels here. We're talking about nuclear energy levels, which means energy levels associated with the nucleus. So there's a ground state, and there's a n equals 1 state and an n equals 2 state. But the thing I want you to notice is that these numbers are in millions of electron volts. So when you have an electron change energy levels in an atom, the electron might lose 4 or 5 or 6 or 8 electron volts. And that energy that the electron loses is balanced by the emission of a photon, and the photon might be visible light or infrared or ultraviolet. But when we're talking about an energy change here that's in the millions of eV, then what that means is that the nucleus loses a lot more energy. It's still balanced in terms of conservation of energy by emitting a photon, but the photon has to have a lot more energy than a visible photon or an infrared photon or an ultraviolet photon. And as a result, the photon ends up being categorized into the gamma region of the electromagnetic spectrum. As an example, let's just say that we have a nucleus. It happens to be cobalt-60. It undergoes gamma decay, and the photon energy is 1.1732 million electron volts. What that means is that the nucleus went from some unstable configuration of nucleons to a more stable configuration of nucleons. And how much more stable is the configuration? It's more stable by 1.1732 million eV. Write the decay equation and explain how the nucleus changes during the decay. All right, so we start off with cobalt-60. The symbol for cobalt is CO, and the atomic mass number is 60. In order for us to proceed, we need to know the atomic number of cobalt. So we're going to have to look at a periodic table. When I look at the periodic table, it might take you a little while because there are so many elements, but after a while you will see where things are. Cobalt is kind of smack dab near the middle of the periodic table, and its atomic number is 27. So it emits a gamma ray photon. This is the symbol for gamma. What's the charge on a gamma ray photon? Well, it's a photon. It has no charge. How many nucleons are in a gamma ray photon? Well, none, because a gamma ray photon is not matter. It's pure energy. And what that means, this is a little weird, is that if the law of conservation of nucleons is true, that means we still have 60 nucleons, and the law of conservation of charge must be maintained. We still have a charge of 27, which means it's still cobalt. But the nucleons in this cobalt here are packed together more efficiently. What this means, everybody, is that the cobalt that we started off with was not as stable as the cobalt that we ended up with. Now, we usually denote that by putting an asterisk on the more excited nucleus. Now, we are asked to explain how the nucleus changes. I'm going to go even further than saying the nucleons are more efficiently arranged. This energy, this 1.1732 million eV of energy, is the change in energy of the nucleus. 1.1732 multiplied by 10 to the 6 electron volts. But change in energy for nuclear changes corresponds to a change in mass times the speed of light squared. And what this means is that when that energy is released, there is a loss of mass. When we did alpha decay the other day and beta decay the other day, we did calculations that showed the mass decreases during those decays. And I made a big deal out of the fact that the reason the mass decreases is because they are exothermic. Well, gamma decay is exothermic as well. So we can go a little bit further and take that change in energy divided by the speed of light squared to get the change in mass. I'm not going to write down a whole bunch of numbers here. I will remind you, though, that we need to convert that electron volt energy into joules. So we have 1.1732 multiplied by 10 to the 6 EV. We have to multiply by 1.6 multiplied by 10 to the negative 19 because that's how many joules there are per electron volt. And we get this loss of energy of the cobalt-60 nucleus. If I divide that now by the speed of light squared, what I can say is that the nucleus lost 2.09 times 10 to the negative 30 kilograms. So in this question, what we can say is the mass of the nucleus decreased by 2.09 multiplied by 10 to the negative 30 kilograms. So just like with alpha decay and beta decay, gamma decay also experiences a decrease in mass because it's exothermic, and that decrease in mass is because matter was converted to energy, and that's where the energy of the photon came from, was the loss in the mass. Let's take a look at something now which is not one of the three main types of decay. There is alpha decay, beta decay, and there is also gamma decay, but there's another type of decay very closely connected to beta decay. It's called beta positive decay. And it's sometimes just referred to as positron decay or positron emission. So what a positron is the antiparticle of an electron. We don't have time to get into a whole bunch of detail here, but there is a collection of particles in our universe which we call matter, and there is another collection of particles in our universe which we call antimatter. So for example, there are electrons, and there are things that can exist in our universe called anti-electrons. Well, it turns out that an anti-electron is called a positron. And what an anti-electron is, or what a positron is basically an electron that's positive. And I know that probably doesn't make a lot of sense, because if it's positive, it's not an electron. But everything about a positron is identical to the same properties of an electron. If you could hold an electron in one hand and hold a positron in the other hand, and you can't, everything about those two particles would be identical, except that the positron would be positive and the electron, of course, is negative. Sometimes these particles are emitted during radioactive decay. And by the way, when they are emitted, there's another particle that goes along with them called a neutrino. So in this example, we're going to learn how to write the decay equation of nitrogen-13 if it's positron decay. So we have to start off by looking at what nitrogen is in terms of an atomic number. Nitrogen is number 7 on the periodic table. It's right here. So now that we know the atomic number of nitrogen, we can start writing the decay equation. It's nitrogen-13 and the particle that's emitted is this particle. It's a positive electron. Now be very careful here. The top number is 0, and if the top number is 0, then there's no protons or neutrons. This bottom number is not a proton, it's charge. A neutrino is also produced. An antineutrino is written the same way as that, with a line over top, so a neutrino just looks like that. And then we figure out what we have left by looking at conservation of nucleons. I need 13 on the top, and I need 6 on the bottom. And then we have to go on a little hunt for what atomic number 6 is, and it's carbon. It's right to the left of nitrogen. So this is the decay equation for the positron decay of nitrogen-13. Now, what is the net change that happens? We did what I'm about to do last time with beta decay. If I count the number of protons, I have 7 protons. If I take 13 minus 7, I get 6 neutrons. That changed to 1 positive electron plus 1 neutrino plus, what do we have over here? We have 6 protons, and 13 minus 6 is 7 neutrons. And when you compare what we have on the left to what we have on the right, we have lost a proton. One of these protons changed into an electron that's positive, which is called a positron, a neutrino, and now on the other side we have an extra neutron. So this is the net change that's occurring when positron decay happens. And again, I'm not kidding myself. You guys already have your final assessment. This is not going to be on your final assessment. So I understand that you may not be too worried about it, and I wouldn't be as a student either. But for completeness sake, again, some of you may go on and take physics in post-secondary. Every little bit I can do to help you out there, I'm going to do. Okay, and there's one final process we're going to look at here I've included this under the topic of radioactive decay, even though it isn't really a decay, but it does involve a change within the nucleus, and it does involve a nucleus becoming more stable as a result of the change. So the process is called electron capture, and what happens is that one of the electrons that is in orbit around the nucleus is captured by the nucleus, and as a result, something changes within the nucleus. We're going to find out what in just a minute, and the whole nucleus becomes more stable. In the process, there's a neutrino produced that's emitted from the nucleus, and then usually there's a short period of time where the nucleus becomes even more stable by emitting a series of gamma ray photons. So electron capture is almost always followed by gamma decay. So the final example, example 5, asks us to write the equation, and I'm loosely calling it a decay equation, for the electron capture of potassium-40. So one of the things that we're going to have to do is locate potassium on our periodic table so that we can determine the atomic number of potassium. When you look at the periodic table, potassium is on the left-hand side of the periodic table. And its atomic number is atomic number 19. So to begin with, what we're going to do is we're going to write out the isotope notation for the potassium-40. It has 40 nucleons, and it has a charge of 19 elementary charges. Of course, we know that's 19 protons, and the elemental symbol for potassium is K. Now, this is what's different between electron capture and traditional decay equations. The particle involved is not produced afterwards. The particle involved, which is an electron, is absorbed. So it is a particle that is added to the potassium before the change. And I'm choosing to use the letter E here for electron. I suppose you could use the beta symbol because a beta particle and an electron are the same, but usually beta as a word and a symbol is reserved for beta decay. And this is not beta decay. You could put beta here instead of E. It wouldn't matter, but I prefer the E. So what do we produce? Well, you're told that one of the things produced is always a neutrino. Now to decide on what we have left, and you can think of what we have left as being kind of like a daughter nucleus. We're going to look at the conservation of nucleons by looking at the top number. The top number on the left is 40 plus 0, which gives you 40. That means on the right-hand side, I need 40 for a total as well. So whatever this daughter nucleus is going to have an atomic mass number of 40. When we look at the charge, which is the bottom number, remember that bottom number represents charge, not necessarily protons. When we add 19 and negative 1, we get 18, and that means we need a total of 18 on the other side. We have 0, so we still need another 18. And now what we're going to do is go back to our periodic table and look up atomic number 18. Atomic number 18 is argon. It's on the other side of the periodic table. So this is the equation showing what happens when potassium-40 captures an electron or undergoes electron capture. The other thing we're asked to do is describe the changes that occur. This is the same type of thing we did with beta decay and also with positron decay. What I can do is I can list the numbers of each type of particle. When I look at the bottom number of the potassium, that tells me that the charge is 19, but I know it's 19 protons. If I want to find the number of neutrons, then what I'm going to need to do is take the total number of nucleons, which is 40, and subtract the number of protons, which will give me 21 neutrons. We also have one electron, and what we produce is one neutrino, and then we have, in the argon, we have 18 protons, And to find the number of neutrons in the argon, I'm going to take 40 minus 18. And I get 22 neutrons. Now, when you look at what's happened here, we have lost a proton and gained a neutron. On the left-hand side, you've got 19 protons, and on the right-hand side, you only have 18. So the net change is that one of these 19 protons combined with that electron that was captured, and it produced the neutrino, plus, on the other side, we have an extra neutron, so plus 1 neutron. So this is the net nuclear change that occurs. And if we had more time in the course, we would have an additional lesson right at the end where we talk about something called the Standard Model of Matter, and we would explain what's actually going on inside of the proton and inside of the neutron that causes this process to occur. But unfortunately, we don't have time for that. So we'll have to leave it there. If you do end up taking nuclear physics in university, you will delve a little bit deeper because this isn't the end of the story in terms of what's happening during electron capture. And you would also delve deeper into beta decay and also into positron decay. There's something else going on. Anyway, that's it for the lesson. On pages 31 and 32 of your handout, there are a number of questions I would recommend doing that involve positron decay, gamma decay, and electron capture. So have a fantastic rest of the day, everybody, and we'll talk to you soon.